I think.
One minute and then we'll start. All right. Hello, everyone. Please take a seat if you are attending the WACI track. All right. Yeah, that's what I like to hear. Oh, lots of excitement. Okay. So welcome everybody to the Wild and Crazy Ideas track, affectionately known as WACI. WACI is a time-honored tradition in the ASPLOS community that frees researchers from the shackles of realism, removes the blinders of short-term thinking, and opens the scientific mind to uncharted frontiers. Since 1998, WACI has been a counterbalance to the conservative impulses brought to us by the traditional peer reviewing process. Today's talks are designed to both be funny and provocative, so please laugh, engage in the Q&A, and enjoy our speakers. First up, we'll be having our keynote speaker, Zach Tatlock. Zach is a professor at the University of Washington who works broadly in the area of compilers, verification, and synthesis. In this WACI track, we often explore bold new ideas that redefine the very notion of computation. And to do this effectively, we must look into the past, to our foundations. And Zach will be taking us very, very far into the past. So please listen as he weaves his tale.
All right. Thank you all very much. One quick thing to acknowledge is that there are some collaborators who have not approved of anything I'm going to say. So all the good ideas probably came from them. Everything else is my fault. So in the debate, we just heard this point that we must return to the foundations. We must understand the fundamentals. And that was really fortunate because the first question I wanted to ask you all is, how do we put a heavy thing on top of another thing? What do you use? There's a bunch of them across the street. I don't know if anybody saw them outside the hotel. Use a crane. That's exactly right. Right? So this is pretty easy. Of course, it immediately begs the question, the crane itself is a big, heavy thing on top of another thing. But of course, we all know the answer to this. You just get a bigger crane. So following, this line of reasoning, I was kind of inspired, and I started wondering, where do machines come from? Since we already know the answer for cranes, maybe we can play the same kind of game, right? If you want to build a really big, precise machine, you probably just get a bigger, more precise machine. But I was actually astonished to find out that that's not the answer. The answer is rocks. And so what I'm going to propose now over the next few slides is a foundation for a programming language based on rocks. Now, the reason rocks are important is they're actually a portal. They are what connects our mathematical knowledge, right? Like Euclid's elements to physical reality. We have all these skills, all these abilities. We know how to prove theorems. We know how to reason about forces and shapes and all this stuff. But what does that have to do with physical objects? Well, we need some kind of known good reference. And traditionally, that's a flat rock. Now, in nature, rocks are generally not flat. They're kind of wobbly. But that's okay, because there's a lot of rocks. So we can take a second rock, and then we just rub that rock on the first. This is known as lapping. And you have to do several, you kind of turn it 90 degrees and you rub it around, you turn it 90 degrees, you rub it around, do it again and again and again. But eventually you reach this kind of fixed point, and then you'll be in one of two situations, right? One of the rocks is going to be slightly concave, the other one slightly convex. Now at this point, it feels like we're stuck. Because remember, I was saying the rock is a portal. It's what connects mathematics to physical reality, and we need a flat surface to bootstrap. I don't know about you, but neither of those look flat to me. So, is it hopeless? Should we give up? Nay, there are more rocks. So we got this far by adding a rock. Let's add one more in and see where things go. So now what we're going to do is we're going to start with 3 rocks. We're going to lap 2 of them together. Then we're going to lap the second with the third. And then we're going to lap the first and the third again. Now let's see, does this actually help us? Did we make any progress here? Well, remember, we were stuck earlier because we had this sort of concavity problem. But things go differently as soon as you have 3 rocks, right? What happens is these are correlated. So, if the green ended up a little bit convex in the first thing, it's going to stay convex, which is going to tend to make the blue one concave. And what that means is by the time you get to the third lapping, the error in the red and blue rocks is going to be the same, which is going to slightly cancel out. You're going to get closer and closer to flat. So actually, we have a process, right? We have hope. We can use all that math we learned in middle school in the real world. Now, you can think about those circles as almost like operators, right? And so you can see where we're starting to think about this as a programming language, right? We can describe how we get from this realm of pure ideas back to physical reality. And I'm sure somebody in the room is thinking, well, wait a second, those things on the far right still aren't flat. But now that we have a programming language, we don't need to despair. I just make it a while loop. And this is actually how it works. So if you go spend $100,000 for like a laboratory grade surface plate, this is how they make it, and make it out of granite. Now, of course, that not flat, how many times we have to do this? Well, it turns out a lot, but the process is error correcting, and over time it will converge. In fact, the only surface that can be common among all three of these is a perfect plane. And so we can do this, and now we've sort of unlocked. We have this achievement where we can achieve flatness, right? So I can bootstrap. If you find yourself on the surface of Mars with nothing, you have to restart manufacturing, grab through rocks, you've got flatness. And what's really amazing, yeah, we've done it. What's really amazing though is that this enables other operations. So suppose you want, I don't know, like a right angle. You can play the same kind of game to construct a geometrically perfect right angle. And in fact, all these things compose. So this really ought to be a programming language. And if you zoom out and you look at the history of industrial evolution, we actually have followed this path, right? We keep developing some new process to really precisely connect our mathematics to physical reality, and that unlocks building some new kind of thing. Now, why did people bother to do all of this, right? We started wondering where machines come from, but why did they build all this? Well, if you go look at the original paper from the 1830s, so all this happened like the last couple hundred years, which is kind of amazing. This is Whitworth's paper on the three-plate method, like how you establish flatness, but it was all to help realize Vaucan's vision of the Jacquard loom, which was sort of manifest in the Jacquard loom. And what distinguishes this is that thing on the right. It's paper tape. It's programming, right? So we did all this stuff because we wanted to have programmable machines. And after a couple hundred years, we have a lot of these amazing tools. In fact, basically everything in this room started its life as a program. And it followed some meaning-preserving sequence of transformations to become a product that then you could go buy at the store. Now, I don't know about you, but something about this image actually rubs me the wrong way. If everything is a program or the output of a program, how come we're not doing that much programming for our actual devices or the things we buy? And the punchline is that ASPLOS hasn't done its job. WACI hasn't led enough. So this kind of novel hardware, knitting machines, et cetera, are incredibly difficult to program. And we're going to skip through the video, but if folks want to see it afterwards, happy to pull it up. But if you go look at how this actually gets programmed, it looks like some kind of level editor for a really bad video game. You actually change pixel colors to control what needles do. Now, my student Amy is intrepid and has even traveled back in time to do original research to figure out how best to program these things, and built some amazing stuff and had some bad adventures along the way. But the truth is that programming this kind of novel hardware remains too difficult. Now, Amy's doing really advanced research stuff. I'm going to speed up a little bit. Happy to chat with people afterward. But there are some tools, some compilers that people use to do things like go from triangle meshes to knit objects, but you lose expressiveness. You can also do this kind of 1D thing where you have full expressiveness, like programming in assembly, but it's really hard to edit. And so we end up in this world where we have these sort of two dimensions. We have these two things. You all know what's going to go right here, right? Tell me. No, it's halide. So actually, it turns out that I really believe that the way we're going to progress fabrication programming languages for things like knitting is thinking about scheduling. And so there's a lot of cool stuff here I'm really excited about. It allows you to decompose. One nice thing about a polygon is that if you split it into two parts, you get two polygons. If you put two polygons together, still a polygon, right? So you have this composition, this ability to reason about things, and you can schedule them separately and compose the scheduled results. So I'm really excited about these kinds of ideas, but this is just one example of what I think could happen with looking at programming novel physical fabrication hardware with the ASPLOS community. So what's going to happen next? Well, who knows? If we look at the theory people with their sort of time cube-like diagrams, we see that it's all about simulating, one machine with another. And so I think what we really need to work toward is a future where it's not just enough to simulate another machine. You have to be able to build the other machine. So we should work towards those programming languages. Thank you all so much. We'll move on to the next speaker.
I think we have time for questions. All right, so maybe we save questions to after the session. In security, the emergence of new threat vectors can have far-reaching implications on how we secure our software system and how we secure our systems. Our next speaker, Guy Wilks, will be introducing BoltBleed, a newly discovered security vulnerability we should all be very worried about. Guy Wilks is a final year undergrad at UC Santa Barbara's CCS computing program, and he'll be starting his PhD at Carnegie Mellon this fall. And he's going to go ahead and get us started here.
Right, HDMI. We're going to look a little less far back in time. We're actually going to look just to a couple months ago. What we're talking about is an extremely important security vulnerability that we have recently discovered. But to understand that, we need to go back to just a couple months ago with Alaska Airlines flight 1282. And I'm not sure you guys can notice, but there's something that is missing from that plane that is usually there. And that is the door plug. Usually they like those to stay on during the flight, but in certain situations they don't. And this is because there were some bolts missing from that door plug. And thankfully, nobody died in that incident, but a couple of phones did fall. And this is a real image on the right and not on the left if you can't tell. And it fell to the ground. And not only did it fall to the ground unscathed, the lightning port was still plugged in as the cord had ripped off as the door plug came off. And you can see it's actually open to the email about the baggage claim for that flight. And if you haven't already noticed it, I mean, what are you doing? This is a security vulnerability. What if there was important information on that phone? What if it had a bank account and information on it? What if it had the next WACI talk on it? This is a problem. To make this a little more illustrative, you might imagine that you had your new framework laptop trademark and you were adding some new RAM mid-flight. So you had opened it up when suddenly the door plug rips open and your framework laptop is falling out the side of a plane going at a cruising altitude of 525 miles an hour, 25,000 feet. And some malicious hacker on the ground knows about this. And they have put a motherboard there that your DRAM simply falls into. And now they have access to your unencrypted next wacky idea. If you haven't noticed already, security vulnerability. Missing bolts in airplane doors risk your data falling to aerial-aware adversaries. This isn't even just a plane issue. I mean, imagine if you were on the Empire State Building and you drop your phone. What if there was somebody waiting on the ground there? Or you're flying on the ever so popular blimp and you drop something. Or you're taking a selfie off the side, off the edge of a cliff and you drop your phone and somebody's on the ground ready. How do we fix this? Well, we have to take lessons from computer science. We have to go from fault detection and fault hardware to fall detection and fall hardware. So we have to start at fall detection. How do we do this? Well, how do we detect anything? Sensors. We start with our accelerometer. When we notice that something has started to fly really quickly, we know something's not right. So then we check our altitude using a barometer. With just these two components, we can tell whether your phone is probably falling out of an airplane. And just to illustrate this, we have microarchitecture ready for this purpose. We take our accelerator and our barometer, and when we notice that a change in acceleration has occurred, we record the first value into a register A. Then we wait a little bit and record a second value of altitude into register B. We do some very fancy arithmetic, and we can see whether you've fallen far enough that a fall has been registered. So now we can detect falls. And by the way, this is foolproof. Nothing could ever go wrong here. And now we have to do something to deal with those falls. So we can do the, frankly, really boring thing of wiping or encrypting the DRAM when a fall is detected. Or we can do the really cool and fun thing where we self-destruct our components when we detect a fall. But first, we have to do our due diligence on the kind of boring part. So when a fall is detected, we can just use some really ultra low power microcontroller on the DRAM stick to encrypt the data or wipe it completely. But as I said, that's really boring. So let's say we just want it to break when it falls. What if we just made a phone that was so bad that when it touched the ground, it simply evaporated? Not only does this require no fall detection mechanism, but in fact, it just works every time. It works for the tiniest of falls, for the largest of falls. It always works. But on the other hand, what if we could just self-destruct our components? So we have some kind of circuit level destruction. We flood our memory circuits with voltage whenever we notice a fall. Or my personal favorite, what if we just cause the lithium ion battery inside the phone to absolutely blow up either via puncturing or causing a short circuit when a fall is detected? I will say here, do not try this at home, nor in a TSA line, or mention any of this in a TSA line. It doesn't end well. So, looking at what we've talked about here today, and pay no attention to the logo or what logo might be under it, these high altitudes are very, very dangerous for your security. And we need to use sensor embedded DRAM in order to patch this and use short circuiting our batteries once we've detected it to solve this. Or the classical solution, just bring a parachute. Thank you.
Let's thank our speaker. We're running a little bit behind, right? So we probably can't take any questions. Is that accurate? We'll take questions at the very end for all of our speakers so that we can just stay on track. So our next, so data movement continues to persist as a hot button issue plaguing accelerators even in today's computational landscape. Our next speaker, Nitesh Narayana, will be introducing GodSpeed, a transceiver-based solution that promises to ameliorate data movement issues. Nitesh is a PhD student at UPC Barcelona, working on improving the performance and energy efficiency of CPUs, and is currently looking for an industry research internship position. So I will let Nitesh take it away. He's going to be presenting via Zoom, by the way. So he is not here physically. He really is eating his own dog food, connecting to the computer via the network. So let's give him a minute to get virtually set up. Okay, yeah, he pre-recorded this, but I think he's online for questions. Is that accurate? Yeah, so.
Come closer, everyone. Today, let me tell you a tale of two researchers who were playing around with a few graphs and stumbled upon something wild and crazy. This tale will supposedly help us understand something about the future technological landscape. Long ago, not so long ago, Nitesh, a PhD student, goes with a few graphs to his friend Abhijit, a postdoc. Let's listen to their conversation. Hey Abhijit, how do you think the processors will look in 2050?
Why 2050?
Because transistors will be 100 years old by then.
Ah, well, I see. With Moore's law now dead, I think the processors will be just playing with cores and chiplets.
Could be, but Intel thinks that Moore's law will continue to live on. Let me show their optimism. Here is an extrapolation of the technology nodes till 2050.
Okay, so the red points here shows that transistors will continue to scale, meaning we may see some crazy processors. But what about the processor clock rate?
I knew you would ask. So, this is another extrapolation of the growing processor clock rate from the Hennessy-Patterson book.
Okay, so it seems that the processor clock has stagnated, which means that the L1 cache bandwidth wouldn't need to increase anymore.
Oh, so maybe that's why they keep increasing the cache size.
Well, you can't increase the L1 cache size much because even a minute increase in its latency might slow down the processor, but L2 and L3 can certainly be increased.
I see, but wouldn't that increase the area footprint of the caches on chip?
No, because transistors are still scaling, remember? Let me show you the extrapolation of the cache area I have collected from AMD Zen series. This projection shows that cache area footprint will continue to decrease.
So you are saying that L1 cache bandwidth need not improve. And there is no area overhead for the increasing cache sizes. So why don't you just put DRAM onto the chip?
First of all, do you think DRAM can give us that kind of a bandwidth?
Not with DDR5, but certainly with DDR-N in a few years. Let me show you this graph here. This graph is a projection that shows DDR-N could achieve 1 Tbps bandwidth well before 2050. And we don't care beyond that for now, which is shown in the yellow. Mind you, this is TBPS, not TBPS.
This is great, except that we can't put DRAM onto a chip due to its capacitor-based storage, as it will burn your chip.
That's disappointing. But is there no way we can make the CPU directly talk to DDR-N?
I think there could be a way. Wireless network on chip, or WINOC, is creating a lot of buzz. If you look at this extrapolation here, WINOC could achieve L1 cache level bandwidth as swiftly as DRAMs. Let me pull out that previous graph for DRAM bandwidth.
Oh, cool. But how about its area overhead?
Here it is. As you can see, it is as low as your cache area by 2050. You don't have to believe me. I'm pulling out the graph for cache area again.
Whoa, perfect. I think I'm cooking up something crazy in my head. Let me show you. We have the sizes. Does size matter? Speeds are coming soon. Wireless on chip, the new knife. We have all the ingredients to cook up something really wild and crazy. You know what happens next. Let's add some craziness. And that's Zachary. Apparate, evading memory hierarchy with GodSpeed wireless on chip. Let me explain. On the left, we have a traditional processor. It meets a request that has to go to the main memory. So first it has to go to L1, it has to go to L2, it has to go to LLC, and then reaches main memory, later coming back as data. This is a long process. On the right is the Apparate magic, where a CPU request apparates from register file to the main memory through while, and the data from the main memory apparates back to the register file. And voila, we are done.
This is crazy, but I do have some concerns. What about the cache coherency?
Well, now that there is no cache involved, the onus of coherency goes down to DRAM. So now the coherency tables find their new home at DRAM.
Will we need prefetching, replacement, etc.?
Now that we don't have cache, that means we don't need any kind of prefetching, nor do we need any kind of replacement.
Okay, but how hot can the chip now get?
Well, we don't have caches to heat things up. Until wireless becomes a hot pot, we are fine. So I present you Apparate, evading memory hierarchy with GodSpeed wireless on chip. So that was the conversation between Nitesh and Abhijit, which concluded with a crazy idea to evade memory hierarchy in future processors. A long-standing dream of computer architecture. Which brings us to the moral of the story. Do we actually need what we already have? Think about it. And if you stumble upon something crazy, feel free to reach out to Nitesh and Abhijit. The end.
So I neglected to mention the second speaker. I didn't realize this would be a team presentation. The second speaker is Abhijit, and they are a postdoc at UPC Barcelona Tech as well. Next up, and so as far as questions go, what we'll do is we'll go through all the talks, and then the remaining questions we'll invite all of the remaining time. We'll invite all of our speakers back to the stage, and then we can engage in a group Q&A session. So for our next talk, we often use metrics to quantitatively assess a multitude of system properties, complexity, performance, fidelity, to name a few. Next up, we're going to have Michael Roitzsch introducing TCB, a bold new metric that will inform the design of the next generation of software systems. Michael leads the operating systems group in Barkhausen Institute and specializes in secure systems using hardware software co-design. And I will let him take it away.
Okay.
Yeah, okay. So hello, I'm Michael. I'm German and I will be your bureaucrat for the evening. So this talk is about bureaucracy in systems. So let me explain a little bit. As systems people, we deal a lot with complexity. Hardware is complex, applications are complex, and in between we have this big chunk, which is the operating system, which accumulates a lot of functionality and also itself becomes very complex. The commonly understood solution to deal with that is divide and conquer. So we end up with something like a microkernel design where concerns are nicely separated. We have these individually components that each become much simpler. We have research architectures like M3, which we built at our institute that even apply the similar ideas to hardware, splitting up the complex hardware into individually isolated tiles. And the general belief is that to deal with complexity, the monolithic approach is considered bad and the microkernel approach is considered good. But is it really? Haven't we just moved the complexity from a few big components on the left side to the complex interaction between many small components on the right side? In other words, haven't we just created a giant Rube Goldberg machine that no one really understands any longer? So do microkernels really make systems less complex? And this is sort of where I see a link between system design and bureaucracy. So let me explain. What do I mean by bureaucracy? By bureaucracy, I mean that the complexity of a process is exposed by the amount of paperwork you have to deal with. If you think about administrative bureaucracy, think about doing your taxes. If you think about systems, a good example could be Kubernetes. YAML files, filling out can feel a bit like doing your taxes. Downsides to this, it's overwhelming to new users, privilege creep due to many interactions between all the small components, confused deputies everywhere, and if we all just give up and admit that we don't understand the system any longer, then in taxes we hire a tax consultant. In systems, it's the equivalent of putting a layer of AI on top of everything that helps us with the systems that we don't understand ourselves any longer. But let's bring this back a little bit to the original question here. If we take this notion of bureaucracy and apply it to these two system designs, the monolith on the left and the microkernel on the right, what do we see? So on a monolithic system, you have the problem that you have a central component that just accrues too much power. And you end up with a system that you don't really want to live in. On the microkernel side, you could say everything gets diluted to a chain of steps that each little step really achieves nothing by itself. And in the end, you don't make progress. So shout out to the people who know both movies. I guess those are the ones getting the joke. And this is even substantiated by publications. So if you look at seriously now at publications, the monolithic design has been critiqued by Biggs et al. In this paper, The Jury's In, famously an A thesis. And the microkernel design has also been criticized by this paper amongst, as an example, which was an NDSS last year from Hugo. He could actually be here. He's at the conference, so if you have any questions. So in the end, we need to actually, we could establish that having too little or too much bureaucracy could be a problem. So in the end, we need to have a measure. We need to find the right dosage. If both ends are kind of bad, we need to figure out some middle ground, and to figure that out, we need to measure. So we need a way to measure bureaucracy in systems. How could that work? So this is my proposal now, to measure bureaucracy sort of as the interaction complexity across interfaces. So if we have components talking to each other, the good case is you have a small interface. If you have a small interface, then the size of the component doesn't actually matter. It doesn't contribute to overall bureaucracy. So this is actually where lines of code as a complexity metric kind of gives you like non-intuitive results. If you have a big interface into a big component, that can be the bigger issue then. And also it kind of behaves transitively. So if you have one component that offers a smaller interface, but then turns around and interacts with many other components, as you do in microkernels, and this kind of spills through the interface, then all of this boundary area becomes your complexity. So this is sort of the intuition that I want to establish as a new complexity metric to replace lines of code as a measure for complexity. We call this the transcompartmental bureaucracy, or TCB for short. Yes, I know the abbreviation is already taken, and yes, that's intentional. You can apply this to all the levels. So you can apply this to hardware. We have hardware componentization efforts that are going on where you could use this. You can apply it to operating systems and to runtime layers. So let me conclude the talk with a call to action. Let's establish this metric, transcompartmental bureaucracy, as a new way to measure complexity, and then go ahead and search the space of, for example, the monolith and microkernel design spectrum for the lowest TCB design. And then finally, take a lesson from politics and publish here at ASPLOS about bureaucracy reduction forever. Thank you.
All right, now for our final speakers, before we move on to the Q&A session. We all agree coming up with new research ideas is one of the hardest and most rewarding parts of the research process. We also all agree LLMs have taken the world by a storm, and automating a number of creative human pursuits that everyone enjoys. So this begs the question, can we use LLMs to come up with new research ideas? Deniz, Altınbüken, and Maas will be introducing BRAINSTORM, a tool that enables us to do just this. Deniz is a research engineer at Google DeepMind, working on advancing state-of-the-art systems using AI. Maas is a research scientist at Google DeepMind that works at the intersection of language runtimes, computer architecture, systems, and machine learning. And without further ado, I'll let them take it away.
Great. Today, I'm thrilled to introduce you to BRAINSTORM, an AI system designed to revolutionize the way we brainstorm and develop groundbreaking research ideas in computer architecture and related fields. As researchers, we understand the unique struggle of consistently generating novel, high-impact, and genuinely out there research ideas. Brainstorming takes immense effort. Combing through vast research landscapes, wrestling with complex concepts, and pushing relentlessly to move beyond the incremental advances that often dominate our fields. This ideation phase, while critical, can become a bottleneck, draining both time and mental energy. To streamline this process, we've developed BRAINSTORM, your tireless AI brainstorming partner. It's designed with one goal: to automate and significantly enhance the idea generation process, allowing you to focus on refining those ideas and bringing them to life. So BRAINSTORM's core is a sophisticated knowledge engine and fueled by advanced natural language processing. It analyzes a massive corpus of existing research, including WACI papers, talks, relevant publications. BRAINSTORM doesn't just skim the surface, it dives very, very deep, extracting key concepts, identifying trends, pinpointing gaps, and establishing relationships between diverse areas of study. From this ocean of knowledge, BRAINSTORM leverages generative AI models to synthesize entirely novel research directions. It explores unexpected connections between seemingly disparate ideas, highlights underexplored areas, and proposes bold new hypotheses. BRAINSTORM can then assist further by outlining research talks and paper structures, and even drafting sections based on the generated ideas. Imagine the possibilities. First, BRAINSTORM can dramatically increase the number and diversity of audacious research ideas explored within our community. We could see a surge in those out-of-the-box concepts that have the potential to truly redefine our field. Secondly, BRAINSTORM improves overall research efficiency. By automating time-consuming tasks like in-depth literature surveys and initial paper drafts, it frees up precious time for researchers. This means more time for designing these experiments, implementing solutions, and pushing those brilliant ideas to their full potential. Additionally, BRAINSTORM has the immense potential to help overcome inherent human biases in the ideation process. By exploring connections our own minds might overlook, it can push towards a more diverse and inclusive landscape of research directions. Of course, with any powerful technology comes ethical considerations that are paramount. We must ask ourselves, is it ethical to present AI-generated ideas without clear attribution? How do we ensure the AI itself does not introduce subtle biases during the idea generation process? It's crucial to maintain human creativity and critical thinking as the driving forces behind research. With AI serving as a supportive collaborator, not a replacement. As a community, we must establish transparent guidelines for using AI in this way. BRAINSTORM represents a significant shift in how we approach research methodology. If we embrace AI as a partner, carefully navigate ethical concerns, and prioritize human brilliance in the process, we stand to unlock new levels of creativity and propel scientific progress in computer architecture and beyond. My hope is that BRAINSTORM sparks a dialogue about the evolving role of AI as a powerful tool to drive innovation. Thank you. So now, to demonstrate the power of BRAINSTORM in action, stay tuned for the next presentation that Martin is going to give. You'll witness firsthand a truly groundbreaking research idea generated by BRAINSTORM itself, a novel approach to quantum garbage collection. Get ready to have your minds blown.
Good evening, everyone. Tonight, we'll embark on a journey into the fascinating realm of quantum computing and its potential impact on a fundamental aspect of computer systems, garbage collection. We'll explore an unconventional idea that might sound like science fiction, but holds the potential to revolutionize distributed computing. Imagine a future where networks of computers operate with the efficiency and coherence of a single machine. Imagine memory being seamlessly allocated and deallocated across this network, without the need for complex coordination or the risk of memory leaks. This vision motivates our exploration of a radical concept, harnessing the power of quantum entanglement for distributed garbage collection. Garbage collection, the process of reclaiming unused memory, is essential for efficient computing. While traditional methods work well within a single computer, they face significant challenges in networks of computers, also known as distributed systems. Coordinating this process across multiple machines introduces complexities such as network delays, consistency issues, and escalating complexity as the network grows. Existing solutions, often involving intricate distributed algorithms, come at a cost of performance and efficiency. This is where our radical idea comes in. Quantum entanglement, a phenomenon where particles are linked regardless of distance, offers a revolutionary approach. Imagine entangling memory blocks across different machines in the network. When a block is identified as garbage on one machine, its entangled counterpart on another could be instantaneously recognized and deallocated. This would eliminate communication overheads and ensure perfect consistency across the network, enabling garbage collection to occur at the speed of light, regardless of the physical distance between the machines. Implementing this idea presents significant challenges. Maintaining entanglement across a network, scaling it to millions of memory blocks, and integrating it with existing computer architectures all require substantial advancements in quantum technologies. Despite these challenges, the potential benefits are immense. Imagine the efficiency and scalability of distributed systems if we could achieve instantaneous coordinated garbage collection. The very notion of distributed computing might become obsolete, replaced by a seamless unified memory space spanning across entire networks.
The implications extend beyond garbage collection. Quantum entanglement could revolutionize distributed synchronization, data structures, and communication, opening doors to a new era of interconnected systems with unprecedented capabilities. While using quantum entanglement for distributed garbage collection may seem like a wild dream, it represents a potential paradigm shift in computing. The challenges are immense, but the potential rewards are even greater. This talk serves as a call to explore this exciting frontier and unlock the true potential of distributed systems in the quantum era. After all, the greatest scientific breakthroughs often begin as seemingly impossible ideas.
Great. Let's thank our final speaker. Now I'd like to invite all of the speakers back to the stage. We clearly planned for this. There's already chairs placed on the stage for our speakers to, answer questions from. And we even anticipated that one of our speakers is remote, and our last talk involves 2 speakers. So I think there's exactly the number of chairs that we need. So I think we just need Zach and. Okay.
Since
Yes.
everything that we talked about was generated by Gemini, and Gemini is our first author, Gemini is attending from there.
Okay, cool. Yeah, we also have Gemini on the
For
computer.
Q&A session.
And if anyone has questions for Nitesh, you can also ask and we'll figure that out. Do you guys want to sit down? I guess I will.
Yeah, that's.
Oh, that's why you guys are sitting up there. I see. Okay. So please approach the microphones if you have any questions for any of our speakers.
So I was thinking that you really are opening the door to, it's pretty obvious who I'm talking about, right? To new advances that are beyond fault tolerance. So have you thought about this fall, not ejection that you can actually follow up on? Have you thought about that? Any ideas about future research in that area?
If I understand correctly.
You just turn it off. Sorry, I turned it off.
If I understand correctly, fall ejection would imply that you don't. Ejection would imply that there's data you don't want. So it just pops out of your computer. The DRAM stick simply pops out of the computer when you no longer want the data, preferably from a high altitude. I think the real question you get there is, does it also get to catch on fire when it falls? And this is, of course, a question that would take many, many years, maybe even decades to find out.
Yeah, thanks for the talk. I have another question about the same paper. Have you considered low altitude falls? For example, if a paraglider pilot drops his phone, that could be very comparable to a very fast elevator. So how would you handle those cases? Thank you.
If the elevator is falling fast enough that it seems like a paraglider fall, maybe your phone should self-destruct. The parameters could be tuned such that only once you hit a certain velocity threshold would your components, I keep saying self-destruct like it didn't suggest encrypting or wiping, but we all know what we want to do. I think the real answer is elevators shouldn't fall that fast. They should make their technology better so we don't.
So for a change of pace, I also have a question for you. Oh, sorry, Nancy.
We're just doing some load balance.
My question is for Gemini. You are a senior graduate student that's been tasked with reviewing this paper, and you don't like it, and you need to show how smart you are. And could you please rip it to shreds?
What was the last part?
Can you please rip it to shreds?
Oh.
And while Gemini is answering that, do you want to answer?
So I also had a question here. I had some issues with the experiments that you presented in the talk. I was wondering if there were other workloads that you also tested against. For example, spaceships famously also have bolts. So I was wondering if your system can work on the moon where gravity is slightly different and falls are not isomorphic to falls on Earth.
We have not tested spaceships. We have tested a machine learning workload, though.
Could you elaborate on what workload that was?
No.
Thank you.
You could read too, but I'll give a summary. So the brainstorm paper has overly ambitious claims. The paper throws around impressive terms like revolutionary and paradigm shifting without providing enough concrete evidence to support these claims. How exactly will brainstorm revolutionize research? It has black box functionality. The inner workings of brainstorm remain largely unexplained. Lack of validation. The paper mentions brainstorm can generate well-structured papers and talks, but these are not validated. Ethical concerns are briefly mentioned, but not deeply examined. And for the quantum entanglement paper, science fiction masquerading as science. This paper takes a cool scientific concept and pushes it to an unrealistic extreme. While exploring the potential of quantum computing is valuable, focusing solely on garbage collection feels like a gimmick. Technical hurdles are ignored. Focusing on the gimmick, not the broader impact. This paper spends most of its time explaining the entanglement idea for garbage collection, neglecting to explore its potential benefits. All right.
Jainil Gandhi Meta. This question is regarding the first talk. Now, most of our processors strive to do things very, very fast. So if we are going to do these things with rocks and we are going to be rubbing them very, very fast to do our computations, is there going to be some fire hazard?
Certainly. I mean, the other thing to remember is that computers are just pictures drawn on rocks. So I mean, that's why you had like lithography, rock lithography, TPU. But yeah, heat dissipation is a major concern. We have a few students working on that, but the quarry is closed down for the rest of the quarter. So we'll please stay tuned for our next paper.
I have a question, a quantum question. I mean, so when we look at this idea of garbage collection, and isn't there an opportunity over here? I'm thinking with the capability of entanglement over long distances, would it be possible, I'm just hypothetically saying, to connect the Indian Ocean to the Atlantic, to the Pacific, and potentially perform garbage collection on all the plastics? Now, if we build a trillion qubit device that would then, through satellite entanglement, enact, would it be possible to perform a readout and potentially just erase all the plastic because it's erased, right? Once we read, is that a feasible experiment?
Fall ejection technology.
Oh, right.
Maybe also ask Gemini to be concise. Okay, yeah, so we have time for maybe one more question and then we have to wrap up. Well,
Hi. I also have a question about the fall detection paper. So I'm worried that this creates a bunch of side channels that can be exploited. So have you thought about the implications of that and how you'll deal with it?
When you say side channel, do you mean like it'll ignite on fire for different amounts of time depending
Yeah,
on how
or
much
if I
data?
like I could tell if my user is on the moon versus Mars. I mean, Elon would be really mad,
Damn. It does introduce that side channel.
But I think in the follow-on paper, you should talk about how you have an automatic defense mechanism, which is that the phone explodes if you do any testing on it, So there's only that much data you can get.
I think it does beg the question, how do you know as an outsider that the phone is falling?
You hear the explosion.
I can assume by the time you hear it, it's close enough to the ground that it is too late.
But you get one bit of info, and we all know we can bootstrap that.
All right, so Gemini says absolutely unrealistic. Entanglement wouldn't work for physical garbage collection. It teleports information, not mass. Needs classical solutions for actual garbage collection. Very concise. It didn't say that.
And with that, we'd like to thank our speakers and thank you all for attending WACI. Please continue this tradition and submit wild and crazy ideas to this track. We rely on the creativity of this community to keep this event going. So thank you. Thanks everybody. Thanks guys. Sorry for the last minute.
Here there is a yeah. No, I mean this is there, but where is the other thing? Where is my goal?
It's for everybody. Yeah, so I don't know.
Should I join?
Oh, there it is. You want to have your laptop over there or?
Okay, great.